Remember, in the last lecture, I've shown you that if the object has planar motion, which means it is only limited to move along two independent directions and rotate about the direction perpendicular to that plane. Here, the plane is xy, so translation x, translation y, and rotation z are the only 3 degrees of freedom. Then we have shown last time that the equations of motion is sum of the external forces on the rigid body is equal to mass times acceleration of the center of mass projected on the x direction, a similar equation for the y direction, and sum of the moments about the center of mass is going to be mass moment of inertia about the center of mass times angular acceleration. Okay, so we have shown those. I've shown you proof of them. And before I start using them and solve problems, I want to talk about this third equation, the rotation equation. So in the rotation equation, you see we are calculating the moments and then the moment of inertia with respect to the centroid. And we have this simple equation from which we can find alpha, typically. Now, the question is, if you remember in statics, for example, you learned that when you have a planar object, if you remember in statics, you have 3 equations of equilibrium. Sum of the force x was 0, sum of the force y was 0, and sum of the moment was 0, but the reference point could have been any point that you choose. Remember? In statics, you said sum of the moments about any point on the plane should be equal to 0, regardless of where that point is. And now I have this question that, now when I say sum of the moment about the centroid is I about centroid times alpha, can I change my reference point from centroid to another point? And let's say the point of reference is any point, point P, and say some moment about P, where P could be on the rigid body or outside the rigid body. Some moment about P is equal to I about P times alpha. Can I do that? And the answer is not for every point. It's not possible to write it about every point. There are 3 types of points about which you can write this simple equation and they work. The first one we saw last time, that is the origin, okay? Which for us here, we assume it as a fixed point, and remember this origin was a fixed point, so what we really can use here is that point should be a fixed point on the rigid body. If there is a fixed point on the rigid body, yes, you can write it about that. Centroid, of course, we know the centroid works, and then if a point is accelerating or decelerating toward center of mass. So the acceleration of the point is toward or away, radially toward or radially away from the center of mass. Like where? Like the contact point of the rolling disc, right? So let me show you these cases, especially because this topic that I'm just talking about is not covered in your textbook. So I want to make sure that you know this material. So case 1 is you have a rigid body, and this rigid body is pinned down somewhere. And I call this point point O. Then, and these are some forces, right? This is F1, this is F2, there might even be a couple here, and so on and so forth. And then I can say sum of the moments about point O is equal to mass moment of inertia about point O times what? Alpha of, let's say, this rigid body. Where for moments about O, of course, we connect point O to where these forces are acting, right? So we use this position vector, we use this position vector, right? So for example, if you call this R1 and call this R2, and this is a couple, so it's free, then this is going to be like R1 cross F1, right? Plus R2 cross F2. You know R cross F is moment. And then you have this C, and since this is clockwise, it's going to be negative c times k, for example, right? And then here, you have to only look at the z component of them because you're writing everything about z. And alpha is clear, but IO is what? We know we typically, when we have objects with fixed shapes, specific shapes like a cube, like a disk, like a sphere, and so on and so forth, a bar, we know their eyes about the centroid typically, right? So if this is the centroid of this object here, I typically know I about the centroid. This is what I can find at the end of a dynamics textbook or a static textbook or a solid mechanics textbook, right? You see those tables at the end of your textbook which have basically section properties and moment tables for different volumes and specific shapes. How do I find IO? You know. What you need to do is to use the parallel axis theorem, right? So if this distance from the centroid to point O is d, then you can say IO is ICM, correct? Plus the mass of the object times d squared, right? Use the parallel axis theorem. Okay, so yes, you can write this equation as long as your point of reference is a fixed point on the rigid body. Also, of course, if this point you want to directly say, no, I want to write it about the centroid, sure, we can do that. Why not? That is what we proved last time. So no problem if your reference point is centroid or a fixed point on the rigid body. The third case is if the point has an acceleration radially toward or away from the centroid. And one case of that we studied was when a disk rolls without slipping, right? If you remember, the contact point had some acceleration if this guy was rotating with a constant omega. Okay, or even, let's see. No, actually, it can have alpha. It doesn't need to necessarily be just constant omega. If you remember, we showed that the contact point has an acceleration. A of the contact point was, magnitude of it was r omega squared, and it was in the j direction. It was toward the center. So if I call this contact point point C, I can also say sum of the moment about C is equal to I about C times alpha. I can also say that. Okay, and again for IC I have to use parallel axis theorem. But I can say this too. But the question is, what about a point here? So a point here in general can have a tangential acceleration and a normal one. So the acceleration of this point is like this. So if I call this point A, or P if you call it, the acceleration of P, first of all, is not a fixed point. It's not the centroid, and the acceleration of that is not in a radial direction toward or away. Away, I mean backwards. Instead of going from point to the centroid, it's from centroid to the points. So it's none of those. So if that's the case, I cannot say sum of the moment about P is equal to I about P times alpha. This is by itself, if you want to write it like that, that is not correct. Okay, and then you might wonder, well, sometimes, again, based on what you learn in statics, sometimes it's easier than that we take our moments about a point that is not centroid and maybe even not fixed. Why? Because at that point I have a bunch of reactions, and when I take moments about that point, that those unknown reactions, they do not have any moment about the point, so they don't show up in the resulting equations. I mean, ultimately from these three equations, we have to start solving for A and alpha and so on, or if A and alpha we can somehow find, we have to solve for probably unknown forces or so on. And which one is typically the one that you start with? You typically start with the one that has minimal number of unknowns. That is the easier one to solve. Ideally, since they are one equation, you will want to always attack the one with one unknown. And so if you have a bunch of unknown forces at that point, you prefer that they don't show up here in this moment term, because typically this alpha is unknown and then you have several unknowns in one equation, which is alone cannot be used. You have to combine it with the others. But if the point of interest has several unknown reactions and you take a moment about that, then they don't show up here and you might get an equation that is easy to solve for alpha, let's say. So sometimes it's more convenient to use a point other than centroid or a fixed point, or maybe there is no fixed point on the rigid body. And you might say, well, like where? Could you give us an example? And yes, I'll give you this example. So here you have a cart, there is a box on it, and somebody is pulling it uphill, and the whole cart has an acceleration a, okay? If you draw the free body diagram of this top part, okay, this member BC, if you call it, this member BC has some reaction from B and C, and then a normal force and some friction from the box. Now the reaction that you have, so let me show you over here, that might be useful. So here, what I am interested is this member BC, okay? This guy here. Not sure if I can get it very easily or not, but I'll try. No, that's okay. So let's say this is that member. Okay, this is this member BC. What are the forces acting on BC? So what you have is two reactions at B, because there is a pin at B, right? So you have a reaction X and a reaction Y. Then there is a normal force from the box. And then basically there is a friction. And then there is a force from C. Now this member AC is a two-force member. It doesn't have a considerable mass. So instead of showing two reactions at C, what I can do is I only show one reaction at C, and I call this force FAC, where FAC is the internal force of that two-force member, and it has this angle, okay, which is 30 degrees with respect to incline, and the incline has 30 degrees, so this angle with respect to horizontal is 60 degrees. And this is an unknown force, and By is unknown, and Bx is unknown. And then from the box itself, if you draw the box, so the box has basically mg, and then it has n, and then it has the friction. And then from the A, you can, if you apply the equations, you can find F, and then if you want it to be like the maximum A that you can apply, then you make this F to be equal to maximum friction, mu S times N, so you can find N. Therefore, in this FBD, you have F and N. And now, if you look at this free body diagram, how many unknowns do you see in it? 3. And guess what? 3 is good. You can solve probably for all three unknowns if you have everything about this rigid body, knowing that this member stays horizontal, alpha is 0, ax you can find from the box, ay, depending on how you define x and y, you can find that, and then you can find the reaction at pin and the force in member AC, right? But now I'll tell you this. So let's say this is the centroid here. I call it C, and this is point B. Now, which point is easier to take some of the moments of the forces about, C or B in this case? Clearly, you see on this member, there is no fixed point, right? There is absolutely no fixed point on this whole object. All of the points are moving. And all of the points have this acceleration A. Okay? So clearly, none of them is accelerating toward or away from the centroid. So you have to either say some MC is equal to IC times alpha. And when you do that, the problem is in that equation, By would show itself because By has a momentum about C and then this other unknown force. So you have two unknown forces showing it themselves here on the left side. And that equation alone cannot give you the number for any of them, even if you say alpha is 0 in this case, which it is. So you cannot find any of these two forces directly because you have one equation and two unknowns. Now, if you want to say some moment about the pinpoint, that's good because if you take moment about pinpoint, you have F and N, and F and N, F doesn't do anything, N does, and N, you know it from the bottom FBD. So the only unknown you will have for some of the moment about B is this guy here, FAC. So you're going to have one unknown on the left side. The problem is you cannot say this is equal to IB times alpha. Why? Because B is a moving point, it's not centroid, and it doesn't accelerate toward or away from point C. So this is not going to work. So although this point is good from the perspective of eliminating unknown forces on the left side, but the right-hand side is not this simple. And then you might wonder, well, is there anything we can add or subtract or do something to this formula to make the equality valid? And the answer is yes, you can. So if B or P is an arbitrary point on the rigid body, arbitrary, with arbitrary acceleration, then yes, you can say some of the moment about P is equal to I of the centroid times alpha, not I about P, I of the centroid times alpha minus R of P with respect to centroid times mass acceleration center of mass. This formula is not in your textbook, but it is extremely useful. So if I have this rigid body, and this is the centroid, and this is arbitrary point P. The mass of this object is M. The moment about the centroid is ICM. Okay, we can find these from the tables. And there are some forces acting on this object. Okay, F1, F2. And let's draw them actually from point P, because point P could be a point of interest. So let's say one of them is here, the other one is here, and then maybe there is another one here too, and so on. So you can say some of the moments about point P actually is equal to, you don't say I about P, you say I about the centroid times alpha minus, and the proof for this I have also provided, I'll show you, I have provided the proof for this in those PDF documents. You say minus R of P with respect to CM cross MACM. Okay, so R of P with respect to CM cross the inertial force MACM. So what does that mean? This is the vector r of p with respect to cm that here we are talking about. It's the vector that connects the centroid to the point P. And it means if you consider this to be a force, and you know it is a force, right? Mass times acceleration is a force. So if you have this force and you put that force basically at point P, okay? If you put it at point P, so this is this force, m times ACM, and the direction of that is the direction of ACM. Then what is this term? It is like a moment, right? Because it's an arm cross a force, right? So this is like the moments of these forces with respect to what? The centroid. Okay, so this is extremely useful, and it allows you to use the advantage of taking moment with respect to P, yet be able to add one extra term on the right hand side and make it happen. And when we get to this, I'll show you how to use it for the sake of maybe this problem. But let me first show you where to find the proof for that, because as I said, you do not need to accept anything in this class from me as is just because I say so. I absolutely recommend you to, it's not in this one, in the other one, look at the proofs. So it should be this guy, I guess. Is it, where was that? Okay. Sure, I've shown it somewhere. Ah, there we go. It's on the second page of this. So here you can see that I have started from the one that we can use. Sum of the moment about centroid is I about centroid times alpha. And then I move forward and prove that some moment about P is ICM alpha minus R of P with respect to CM cross MA CM. Okay, so, and it is not really hard to show that proof. Just wanted you to take a look at that, and I can go over that, but I would rather you take a look and we can discuss in the classroom if you have questions about it. So it is on the second page of this proofs of rigid body kinematics and kinetics. Take a look at that. Okay, so now that we have seen these formulas, you might wonder, okay, how do I really use them in practice and solve something with them? So here we have 4 problems at the end of this chapter, 2 examples and 2 end of chapter problems. And I marked 2 of them with red stars, so we do it in classroom, especially this one that is a significantly time-consuming problem. And then the first one, which is an easy one. So what I would like to do with you is to solve problem example 18.3 and then problem 18.2. Okay, so let's look at these 2 problems together. Then we do a lot more in the classroom. So here you have a mass, slender bar, mass m and length L. Currently it has angle theta with respect to the vertical direction, and it has an omega. Counterclockwise, you want to know what is the angular acceleration at the moment. Okay, so you want to find alpha at this moment. And it's all parametric. There is no number here. You have to solve with parameters. Okay? So this is our problem. And the problem is simply asking about alpha. So what we do is we use the traditional XYZ. So this is our x-axis, the y-axis, and then z to be out of the plane. Okay, and then we need to draw the free body diagram. So if that is your object, you have a force here, right? A normal force. I can call it N. And let's give some name to these contact points, if you don't mind. So I would call this contact point point A. I would call the centroid C, and I would call this other contact point B. So there is one A here that you can see, and I can call it like N sub A if you want. There is another normal force at B, and I can call that N sub B. There is the force of gravity, mg. And then if you look at the problem, it is said it is sliding on the smooth floor and wall. So it means there is no friction on the contact points. If there was a friction on the wall and the floor, since this guy is rotating counterclockwise, point A is moving to the right, therefore friction would be to the left. B is going downward, so friction would be upward. If there was friction, in this case there is none. Okay, so I assume that is quite self-explanatory. Let's make this guy a little bit smaller, maybe even more. No, 20, not 200. There we go. And then here we have three governing equations, which says sum of the forces in the x direction, which in this case the only force we have is NB. This is equal to mass of this object times acceleration of point C along the x direction, some forces in the y, which is N A minus mg is equal to mass times acceleration of point C in the y direction. And now you can take some of the moments about what? You know A and B are not fixed, and in this case, these 2 points do not have tangential acceleration because omega, or actually they do because alpha is not 0. So they are not really accelerating or decelerating toward point C. They have both normal and tangential acceleration, so the resultant acceleration is not towards C. So I cannot simply use A and B. If I want, I have to use this modified formula I just showed you. So right now, just to start, I'm not going to go about A or B, I'm just going to go about C. But you clearly see the problem. When I take moment about C, what happens? In this, both NA and NB, which are unknown, right? You know, both of these guys are also unknown. They would show themselves. But as I said, for the moment, let's assume that we can solve a, let's say 3x3, or in this case, maybe a 5x5 system of a 3x3 system of linear equations. So we know this is about Z, and we know about Z is counterclockwise positive. Now, what is some of the moment here about point C? So NA has a moment about C. Clearly, this is counterclockwise, right? If you have a car here and you have a center of a traffic circle, it has to go counterclockwise about the point C, so it is positive. The distance between them is this distance from here to here, which is basically L over 2 times sine theta. So it is going to be L over 2 sine theta times NA. NB is clearly clockwise. The distance is this vertical distance, which is L over 2 cosine theta, and it is negative. And the gravity doesn't do anything. This is equal to I about the centroid times alpha, and you know I about the centroid for a slender bar is ml squared over 12, right? So hopefully you all know that. I assume you all do, right? If you don't, please keep that in mind. If you have a slender bar with mass m and length l, okay, so this is a slender bar. the length is L, the mass is M. If I call this point A, and if I call this point the centroid, the mass moment of inertia about C is ml squared over 12, and the mass moment of inertia about one endpoint, either A or B, doesn't matter. So A is equal to the same thing about B, if this is symmetric, of course, right? So this is like L over 2, and this is L over 2. Assuming that this is symmetric, this is going to be ml squared over 3, which you can easily show by the parallel axis theorem. So keep that in mind, that is important. So now we have 3 equations, but how many unknowns? Well, I don't know NA, I don't know NB, I don't know alpha, and actually at the moment I don't know ACX and ACY. What are those? No mention of them in the problem. So what should I do? I have 3 equations and 5 unknowns. And by the way, as I said always, a good practice is to number your equations. So give them a number. So I have 3 equations, 5 unknowns, and I don't have any more kinetics equations. Kinetics is dead end. What should I do? If you remember from one of my previous lectures, I mentioned that whenever kinetics is dead end, what would you do? You resort to kinematics. What do I mean? It means try to find ACX and ACY from kinematics for this object, or at least relate them to other unknowns of the problem. Of course, you cannot relate them to NA and NB, because in kinematics the forces never show themselves, but you might be able to relate them to alpha. So if these two are functions of alpha or related to alpha, then they are not really 2 additional unknowns. Basically, all you have is NA, NB, and alpha, and then you have 3 equations, 3 unknowns from which you can solve for alpha. So first, can I relate ACX and ACY to alpha? Yes, probably. So if you know, in kinematics, we can relate the acceleration of 2 points on a rigid body together, right? Any arbitrary 2 points. And here, one of the points should definitely be point C because I'm interested in it, and then one of the other points should either be A or B. Why? Because I know something about A or B. A only moves horizontal, B only moves vertical. So first, let's relate C to maybe B. So I say A of C, and this is the kinematics formula that we had, is A of B plus alpha cross R of C with respect to B minus, again, since this is a 2D case, I can simply say minus magnitude omega squared times R of C with respect to B. I'm not doing the double cross because this is a simple 2D case. And then, now what? What is A of C? Well, I don't know, but I called its components ACX and ACY. So this is going to be ACX times I plus ACY times J, right? What is A of B? Again, I don't know its magnitude, but I know B only goes up and down, so I call it AB times J. Now, if it's negative, which in this case it could be, then I end up with a negative number for this. So that's fine. Alpha here is, again, I don't know, but it is either positive K or negative K. So I call it positive. It might end up negative. That's fine. Omega is omega. It's just a parameter that is given to us. So it's a given one. And R of C with respect to B is what? It connects B to C. It's this vector. If I can draw it for you here, it's this vector. Okay, sorry. This is R of C with respect to B, and if we need, this is R of C with respect to A. Okay, so if I want to write it as a vector, it has a length of L over 2 angle theta, and it goes down and forward. So it is going to be L over 2 sine theta I, and this minus L over 2 cosine theta J. Good? Then what I can do is I carry out this cross product, which is K cross I and K cross J, multiply this constant by A and J, and now if you look, I have an equality. Two vectors are equal, so I say the I's are equal, and then what? The J's are equal. And if I do so, I get two equations. For I would get a C of X on the left is equal to, on the right you have K cross J, which is negative I, but you have another negative, so you would get positive L over 2 alpha cosine theta, and then minus L over 2 omega squared sine theta. And then you can show that a CY, the J component, is equal to AB, and then you have K cross I, which is J, so it is going to be positive L over 2 alpha sine theta, and then you want to get positive L over 2 omega squared cosine theta. So these are the two equations that you would get. Now clearly you see the top equation is relating one of the unknowns that I had here on the top, ACX, to what? To the other unknown alpha. The other term here is a constant, is a known term, not constant, is a known term, because omega and theta are given parameters. Okay, so here theta should be considered what? A given parameter, and omega should be considered a given parameter. So the top equation is amazing. It gives me ACX related to alpha. So I'm going to use this. I'm going to directly call this equation 4. That's a good equation. What about 5? 5 seems like it is relating my ACY also to alpha. So it looks like good, and omega is known. The only problem is AB. If I want to use the bottom equation to also eliminate ACY in equation number 2 based on alpha, the bad thing is this guy here gives me one equation, but it brings in what? One more unknown. So now instead of 5 equations, 5 unknowns, I'm going to have 5 equations, 6 unknowns. So because this guy contains one more new unknown, I'm not going to use this. I say, well, it's not useful for me. Okay, because I just want to bring more equations, not more unknowns. What I'm lacking is 2 equations. I got one of them, 4, that is amazing, but it's over. I cannot do anything more. But I have one more point that I can relate to C to, and that is point A. So I can relate C to A now and say, well, A of C can also be written as A of A plus alpha cross R of C with respect to A, and minus omega squared R of C with respect to A. And then again, A of C is ACX I plus ACY J. A of A I don't know, but A only moves horizontally, so I can call it AAI. Alpha is again alpha K. This omega is known, and R of C with respect to A, if you look at it, it is going to be negative L over 2 sine theta I plus L over 2 cosine theta J. Okay, this vector in purple. And again, here you have equality of 2 vectors, so you set the I is equal and you set the J is equal, and if you do so, you're going to get ACX based on AA, which is not useful. I write it for you. I don't need to write it even because I found something for ACX already, a good one. And this one is going to add AA, which is another unknown. So this is not going to go anywhere, okay? Although I write it for you, but just keep in mind, it's not going to go anywhere. So this is going to be minus L over 2 alpha cosine theta, and then plus L over 2 omega squared sine theta. And then you can find from the equality of y's, ACY is equal to, so it is going to be K cross I, which is J, and then you have a negative. So you're going to get negative L over 2 alpha sine theta. And then you have negative and negative, so you're going to get another negative. As I said, the top equation is not useful, but the bottom one is, because it relates the unknown ACY to the unknown alpha and the known term L over 2 omega squared cosine theta. So now with 1, 2, 3, and 4, and 5, I have 5 equations, 5 unknowns, and I can solve. Okay? Now, this problem, as I said, is not a simple problem. You have to basically use all you know from kinematics and kinetics in order to solve this problem. But if you do, now how do you solve it? So 1 has ACX, so you're going to plug in 4 into 1. 2 has ACY, so you're going to plug in 5 into 2. And then 1 and 2 becomes equations which only has NB as a function of alpha and NA as a function of alpha. And then those resulting equations you plug into what? 3. So it's going to be all alpha then. And then from that equation you can solve for alpha. Okay, so this is how you do it. You're going to plug in 4 into 1. You're going to plug in 5 into 2. And then the result of them will go in 3. And then you have to solve for alpha parametrically. If you do, actually, you're going to get a bunch of simplifications. And it's not going to be super bad. This is the final answer. Alpha is 3g over 2l sine theta, okay? So clearly you see alpha at the moment is not even constant. It depends on the sine of the angle. And so as the bar slides down and theta increases, sine of the angle increases, and so alpha is increasing. So this is not even constant alpha. This is a variable alpha. And if you know, alpha is what? Alpha is theta double dot. And if you remember, this second order differential equation has no analytic solution. This is very similar to the pendulum equation. Do you remember? The pendulum equation was theta double dot was negative g over L sine theta. So this is very similar to a pendulum. Okay? So the equation of motion for this guy has no analytic solution. In other words, if I give you two initial conditions, theta at 0 and theta dot at 0, okay, so if I give you these two conditions for omega at 0, you can never give me theta of t as an explicit function, okay? There is no analytic solution at the moment in math. You have to solve it numerically, and we have done it in Simulink in the past. Okay, so you see the simple problem of a bar sliding on the wall and on the floor, even without friction, is quite complicated problem. But that's how it is. And it is even 2D. There is no 3D that we have considered here. So that was this example. Hopefully you got it. And if you have questions, please always ask me in the classroom or during office hours. The other problem we are going to solve is this problem of somebody moving a fridge. Okay, this is a good problem if you have a moving coming on, right? Or you want to help somebody. So you want to move the fridge, you apply 30-pound force to the right. The fridge is 230 pounds. The coefficient of kinetic friction is 0.1. You want to find what is the acceleration of the fridge as a result, and then what are the normal forces at A and B applied to the fridge. Okay? The problem can be solved very simply if we neglect a bunch of details, but I don't like to, so you're going to see me go over small details of this, which we have to investigate and then solve the problem. So let's handle this case here. And let's see if I can just get the fridge. Okay. So this is the example. And there is a force of 30 pounds. And here when it says pound, it means pound force, of course. Applied. The weight of this guy is 230 pounds. When it says a fridge of 230, it is pound force. It is not pound mass. If it's pound mass, then it says so. So when your textbook doesn't say anything, you assume it's pound force. You have a friction, and then this distance is 60 inches. Okay, so mu k is 0.1. You need to find A, and you need to find N at A and N at B. And again, as I said, this distance from here to the floor is 60 inches. Okay, so this is what you need to solve in this problem. Okay, so in this case, we first need to draw the FBD. So we have F, we have the force W, of course. And then we have a reaction in A, and then we have a reaction in B, and if this guy is moving forward, there is a friction, so there is a friction here, Fk at A, and then there is a friction here, Fk at B. Okay, so that is your FBD. Your coordinate system, you choose the traditional XYZ. That's sufficient for here and the simplest. There is no reason to go for more complicated choices, so that should be good enough. And then what we want to do is apply our equations of motion. So if we apply them, we have sum of the forces in the x direction, which in this case is F, minus Fk at A minus Fk at B. This is equal to mass of the object times acceleration of the centroid at points in the x direction. And centroid, we mean this point C here. And this point is A, and this point is B. Clearly you can see that's B here. If you want, I can leave it here as B, and this is the centroid C. Then we have sum of the forces in the y direction, which is going to be NA plus NB minus mg, or minus W if you want to call it. is equal to mass times acceleration of the centroid in the y direction, and then sum of the moments about centroid is equal to, in this case, which forces create moment about the centroid? Actually all of them except for W. F is clearly clockwise, so it is going to be negative F times the distance between C and F is 60 inches minus 28, so it is 32, and we divide it by 12 to convert it into feet. Then N, the NA is also clockwise. The frictions are both also clockwise, so there's going to be minus NA, and the distance is 14 inches. NB is positive. That is also 14 inches. The frictions are both 28 inches, and they are both negative. Is equal to I about the centroid times alpha. So now I have my three equations, and now it's time to, before we even start to do anything, and it's always, again, it's a good practice to number equations, so I call them 1, 2, and 3. It is always a good practice to see how many unknowns and how many knowns we have here. So F is 30, that's good, I know it. NA and NB are unknown. W, I know that's 230. Then mass I can find. Alpha is unknown. Acceleration CX and CY are unknown. IC I don't know because the specs are not given. I don't know the total length of the fridge and the mass distribution, so IC I don't know. Mass we have to find. Okay, remember that here it's weight, not mass, so mass is W divided by G, and W is 230, I'm sorry. And when we work in the British system, G is 32.2. Okay, so we get that. You're gonna get 714. So we can use that here. Now the question is this. So clearly you see I have a lot more unknowns than knowns, or the equations. First of all, how do we know that this 30 pounds is enough? So the good step is to do is, before I do anything, first I get rid of this K. And just call this FA and FB if you don't mind. Because how do I know that with 30-pound force I can move them? Maybe that's not enough. So we cannot always assume that the system will move. Yeah, the problem says what is the acceleration? Well, it could be 0. Right? It could be 0. Maybe the system cannot even move. So it doesn't move, it doesn't start a 0. So first thing is, I have to find out whether the 30 pound is enough or not. How do I find it? Using that mu k, and actually here you need to have mu s, not mu k, right? So remember, you always need to compare the driving force, which is 30 pound in here, against the maximum friction that the surface can generate. So if I knew mu s, I would multiply it by all of the friction that the surface can generate. Clearly, all of the friction here is, all of the normal force here is NA plus NB, right? Because there is one thing I know for sure, this guy is not going to fly vertically, okay? So ACY is not really an unknown, it is actually 0. So from equation 2, I can definitely know that Na plus Nb is equal to 230. And when you multiply this summation by mu s, it's going to give you the total friction, right? And then you compare it against 30. So if mu s is equal to mu k, which is not, typically mu s is bigger, so 0.1 times 230 is 23. 23 is less than 30. The system will move. But the problem is this question never gave you mu s. So here we have to assume something. I mean, the problem statement is not the best, but we assume here that the system does move. Okay, so here, let me write it for you. We assume that mu s is less than f divided by Na plus Nb, which is less than 30 divided by 230, which is 0.13. So as long as, in this case here, the static coefficient of friction is less than 0.13, then I can say that the system does move. Then my frictions are going to be simply what? This is going to be Na times mu k. This is going to be Nb times mu k. And similarly here. So good, at least the friction terms are known. They are not new, other extra unknowns. They are known. That's good. Now, good. It does move, so AC is not equal to 0. The frictions are kinetic frictions. What about alpha? How do I know that this fridge is not going to tip over? How do I know this guy is not going to rotate? Because you have probably done it, right? You moved something tall, and the friction between the object and the floor was high, and you pushed quite strong, and you saw that instead of the object going forward, it tipped over. So how do I know in this case whether alpha is 0 or not? Well, I have to find out. It's not just assuming everything. So let's say for a moment that this force and the distance of 60 inch is large enough to tip this guy over. So it's about to tip over. If it's about to tip over, what happens? It is going to rotate about which point? Sure, about point B, right? The front leg. So the fridge is going to tip over and rotate about point B and rotate, right? Spin. So here the question is, what happens to the reactions Na and friction A if the fridge is about to rotate about B? So if it rotates about B, what happens to the contact at A? Right, you're going to lose the contact. And when you lose the contact at A, because this leg is going to get off the ground, you're going to lose what? Both of the forces, Na and Fa. So all you will have is going to be Fb, Nb, W, and cap F. Now, under what condition this system will rotate about B? You know, if it wants to rotate, it has to rotate what? Clockwise, right? And if you want to have a rotation clockwise about point B, some of the moment clockwise about B has to be what? Positive, right? You have to have a total clockwise moment about B, which makes that rotation happen. So what you would do is, you say if the fridge is about to rotate about B, it will lose contact at A, i.e. FA equals NA equals 0, and let's say rotate clockwise, right? We know that's the only way that it goes in this case. So that's it, and we need to have sum of the moments about point B in a clockwise positive or in a clockwise direction to be what? Positive. If that's the case, yes, then it's gonna happen. But let's calculate it, see if it's positive or not. So what is sum of the moment about point B? So if we go back, get rid of these two forces at A, the only two forces that create moment about B is the weight and F. The moment of F about B is clockwise, the moment of W is counterclockwise. The arm from F to B is 60 inch, the one from W is what? 14 inches. So it is going to be F times 60 inches minus W times 14 inches, right? If you want, we can divide them by 12 too to convert them into feet, but it's not going to change the sign. But F is what? 30, and W is what? 230. And if you calculate this number, you clearly see this number is 1800, and this number is way more than 1800, right? This is more than 2000. So actually, sum of the moment is negative. So you will never get a positive clockwise moment about B to make the rotation happen. So it is not going to rotate, therefore, alpha is what? 0. So this guy is not going to tip over. Why? Because your force was not big enough, and or the distance from the bottom was not high enough. So in this case, it's 14 times 230, okay? 14 times 230 divided by 30. So let me show you. If here, 60, right? 14 times 230 divided by 60. 54. If you applied 54 Newton, or pound force, I'm sorry, if you applied 54 pound force instead of 30, you would easily tip it over. Okay? So your force was not enough. Or if you made this 60 inches quite taller, probably 90 inches or so. But, well, you have to see if this guy is 9 inches tall itself. But clearly in this case, if I go back to my governing equations, now I know alpha is what? 0. Therefore, I don't even need to know I, because the right-hand side is what? 0. That is good. And now if you look at your equations, how many unknowns do you have? Clearly, all you have unknown is NA, NB, and what? ACX. The rest of them are basically 0 or known. And therefore, if what you can do is, if you basically, because if you look at equation number 3 is only between NA and NB, right? Everything else is a known number. So 3 and 2 have only NA and NB, nothing else. So from 3 and 2, you can directly solve for both. And once you plug them back into 1, you can find what? ACX. So I write that solution for you here. So from 2 and 3, if you solve, you will find that NA is equal to, and NB is equal to, and the numbers are 80.7, 149.3. So 80.7, 149.3 pound force These are this, and then when you plug these back into 1, you will see that the acceleration of the fridge in the x direction is going to be 4.2 feet per second squared. Okay, so please never always assume that everything is there. Yeah, this is not going to tip over, it is going to move and everything. No, we have to investigate that. But once we do, then we can solve the problem properly.